Okay. Uh, Now it's 1 p.m., right? So I think everyone want to have lunch first. So I will finish the slides as soon as possible, maybe in 10 minutes or shorter than 10 minutes. Okay. I'm Zhi Wen Chen, a postdoctor from U of T. This is my professor, Professor Singh. Today I will show our recent work, theoretical design of high entropy alloy catalysts. As we know, the development of HA is very rapid, and they have so many advantages, such as high entropy effect, Fridge effect, Scaling diffusion, and cocktail effect. All of them are useful for catalysts. So this is why we do DFT calculation for the HA catalyst. Now we do HA catalyst, but so we should know the challenges of the HA catalyst. The bigger problem is unclear structure activity relation for HA catalyst, because the surface of HA is so complex. So it is difficult to fully capture by experimental by experiments. So we think a DFT calculation can display the active center. However, it is time consuming to capture all possible active center for HEA. So maybe machine learning is the answer. Our group does a lot of work on HA catalysts, mainly exploring machine learning and DFT calculations. Also, we collaborate with some experimental experiments and resolving these published papers. In the morning, Professor Singh have so lots of work on machine learning part. So now I will only show this this paper. Okay. So to address the energy crisis and environmental pollution, hydrogen energy is of greater concern, including hydrogen generation, hydrogen storage, and hydrogen application. There are so many catalyst process among this hydrogen energy. So therefore, exploring catalysts with high catalytic performance is impractical. However, the traditional catalysts follow the that means the catalyst with high catalytic performance should have not too strong, not too weak absorption. This is why PT has the best catalyst for hydrogen evolution reaction, because the absorption energy of hydrogen on PT surface is nearest to zero. Now we think how to. Now the question is how to reduce the cost of PT based catalyst without losing catalytic performance, or even further improve the performance. Our strategy is taking HEA as the catalyst for HER due to because more active centers on HEA catalyst, and second, we choose this this ACE system as a catalyst because first these elements are non-noble metal. Second, this element at the two sides of this volcano. So it's as because the surface of HA is very complex, resulting that its nodal value it should be include many values. So that means the descriptor for the absorption energy of hydrogen near to zero doesn't work for HA catalyst, and the Sabatier principle is no longer valid. So in our work, we will explore new descriptors and new mechanism for HA catalyst for HER reaction. First of all, we plan to consider all possible absorption sites on HEA for hydrogen, including as shown here, including bridge sites, hollow sites, and as well as the different metal. We found the electron distribution of HA surface is variable due to the different metal sites. That means the sites. That means some sites should have strong absorption, while some other sites have weak absorption. So we can use the site with strong absorption for the activation of water. The site with weak absorption for the formation of the H2. The adsorbed hydrogen linked to these two kinds of sites. Therefore, we proposed a new mechanism and usual Sabatier principle. That means for a good HA catalyst, the site with strong absorption should be stronger, and the site with weaker absorption should be weaker. That so this is very useful for hydrogen evolution reaction. And then we consider the Zhi Wen effect in the electro structures, as shown in figure A, and we can see that with increase the compressive strength, the d-bond center will be more negative. That means the absorption energy will be weaker. And then we calculated the absorption energy distribution on HEA surface. We can get the same conclusion. The more strength, the weaker the absorption energy, as shown in figure B. So we know also we found the relation between the strength, the d-bond center, and the absorption energy. That's so, and also we can see that the absorption distribution follow similar Gaussian distribution like this. So we use this Gaussian distribution as the new descriptor to indicate the catalytic performance of HA catalyst. And then we consider the reaction mechanisms for HA on HA and compared with the best catalyst PT111. There are two mechanisms. The first one is the warm hydroxide reaction. We can see that the for the PT11, the potential limiting step is the hydroxide step with the reaction free energy about 0.7. But on HEA surface, we can see that if we consider the hydrogen diffusion, there is no potential limiting steps on HEA surface. These two steps are easy to handle, and for the diffusion for the hydrogen diffusion region 1, we can see that in figure C, the vary is very small, about 1.1 to 1.2 eV. Also, for the second mechanism, warm Tucker slab mechanism, we also found the catalytic performance of HER on HEA is still better than the PT111. Also, during the whole reaction process, there are a second diffusion region. The line is the barrier is about 0.3. It's very small. So based on the DFT, we know the HEA catalyst should have high catalytic performance than PT111, right? So and to prove our idea and the DFT result, our partner synthesized the HEA catalyst, and they found hydrogen spillover on HEA surface, and the catalytic performance is very good, better than most of the reported values. Also, we consider the carbon, oxygen, and nitrogen diffusion on HEA surface, and we found the absorption distribution of this also follow Gaussian distribution, and the barrier of the barrier below 1 eV. So maybe this idea can also extend to other carbon related, oxygen related, or nitrogen related reactions. So this is the conclusion. From the science part, we proposed an unusual subtle principle with a new descriptor, and in the performance, our insight was further verified by experiments. The design HEA catalyst has a very good catalytic performance, and future work, we know that this is a new idea. There might be many issues for this idea. So we will continue to do this work. Our idea has shown potential to attend to other reactions, including these reactions. Okay, thanks everyone in progressing the group, and thanks the funding from NRC Department of MSE. Thank you.
Great. Are there any questions? Just what's the 5.10%? This you had some percentage on your HEA alloys, and I wasn't sure what they were.
5%.
So when what's the percentage if you go on this graph?
Oh, yes.
What does that mean?
Oh, it means string. For example, the lattice is 100. 1% means 99.
So 6.8 is huge.
Yes. Yeah,
I mean,
yeah,
non-physical.
yeah, yeah, yeah.
Okay.
Are there any other questions? In which case, let's thank the speaker again and thank you.
Even so,